Alright, so I wanted to make a video to answer the question here. This is 6.4, number 23, or the worst problem in the world. Find an equation for the tangent line at the given point in the curve. And this is pretty intense as far as keeping track of stuff. I was amazed that I got it right on the first try. So here's what you do. You're going to use implicit differentiation to differentiate both sides. The idea being you're thinking about y as a function of x in this, okay? And clearly x is a function of x, and so what you have to do is kind of think of the left-hand side as a function of x, the right-hand side is also an equal function of x, and equal functions have equal derivatives. That's why it kind of makes sense to take derivatives of both sides. So that's what we did, is we take derivatives of both sides. They both involve using things like the chain rule and the product rule. On the left side, just to quickly step through it, on the left hand side it's just a chain rule to start, so it's differentiate the exponential and then the stuff up in the argument, and so the derivative of the 2x squared is 4x plus the derivative of the 2y squared, and that gives us 4y times y prime, and this is a use of the chain rule that comes up when we do implicit differentiation, and it's if you take an x derivative of a function of y, then it's the function's y derivative times y prime. And so here's our, so that's our left-hand side. The right-hand side is very similar. In the first term here, the x e to the 29y, it's a product of two functions, so it's really the product rule. So derivative of x is just 1. That's what gives me the first term. Then derivative of e to the 29y, I get 29y prime from the chain rule, x e to the 29y. And again here it's a product rule. I don't want to step through the entire thing, but differentiate the first thing. That's this 2y prime times the second. Carrying the minus sign through, that's why I have a minus here. 58/5 comes from the chain rule, etc. So we have taken a derivative. Now the idea is to isolate the y prime. So I do that by taking all the y prime terms. There's one of them on the left hand side and two of them on the right, and I put them all together, factor out the y prime. Okay, and we've got this big ugly equation in x's and y's and y prime that has to be satisfied. Okay, now the goal is to figure out the equation for a tangent line to the curve given by that original equation at the point 5, 2. So I basically need y prime evaluated at 5, 2, and the student who asked this question actually came up in the context of, man, I get these big exponentials when I plug in 5 and 2, and that's true. You end up with e to the 58 all over the place here, but the point is you actually get e to the 58 on every single term. So you could just actually divide through by e to the 58 and it goes away. Okay? So when I solve for y prime, it just ends up being this big ugly looking fraction. I'm sorry for the mess. I actually didn't expect it to be right the first time I did it, so I didn't even try to write it down very carefully. But it was right. So my y prime, when I simplified this big ugly fraction, was 327 over 665. And then I just plugged it into the point slope formula, and I figured out my my y equals mx plus b equation. So that was it was a really difficult computation, but the question that the student had asked was, how do I deal with those large exponentials? And my answer to dealing with large exponentials like e to the 58 or e to the 2000 is, well, if it's beyond the scope of the calculator, look and see, number one, was the question well posed, and secondly, was there some kind of mistake where you didn't actually need to evaluate such a large exponential? In this case, we didn't really need to evaluate the large exponential, and that's what allowed us to do the problem.